Welcome to Grade 9, where every chapter becomes a journey of discovery. Stay until the end and understand every textbook concept with ease. Like, comment, and subscribe for daily learning. Visit rehanstudio.com for new CBSE practice questions and exam success.
We have explored how scientists describe motion using observations, measurements, and graphs. Distance, displacement, speed, velocity, and acceleration help us understand every kind of motion. Whether objects move in straight lines or circles, science helps us everywhere around us. Understanding it helps us understand the world itself.
You can also calculate the magnitude of velocity from a position time graph. Beyond position, the graph also gives velocity through its slope, its steepness. In triangle ABC, side BC represents the change in position, S2 minus S1, and AC represents the change in time, T2 minus T1. The method: pick 2 points on the line and make a right triangle. The vertical side, BC, is the change in position, and the horizontal side, AC, is the change in time. Average velocity equals BC divided by CA, which is S2 minus S1, divided by T2 minus T1. Divide the vertical side by the horizontal side to get the velocity. Rise divided by run. By heart, velocity from a graph equals change in position divided by change in time equals the slope. Example: V equals 80 minus 40 divided by 4 minus 2, which is 40 divided by 2 equals 20 meters per second. The work: substitute the values. 80 minus 40 divided by 4 minus 2 gives 40 divided by 2, which is 20 meters per second. BC over CA is called the slope of the line AB. The ratio, vertical divided by horizontal, has a name: the slope of the line. By heart, slope equals rise divided by run. The slope of a line is the steepness of the line. Simply, slope measures how steep the line is. A steeper line has a bigger slope. The slope of a graph gives the rate of change of the y quantity with respect to the x quantity. A general rule for all graphs: slope equals the rate of change of y with respect to x. For a position time graph, that rate is velocity. Example 4.6. A line parallel to the time axis means the object is at rest, stationary. A flat horizontal line on a position time graph means position is not changing, so the object is at rest. By heart, a flat horizontal position timeline means the object is at rest. Example 4.7. A steeper position timeline means higher velocity. Object B is faster than object A. A comparison rule: on a position time graph, the steeper line belongs to the faster object. So if B's line is steeper than A's, B is faster. 4.2.3. Velocity time graphs. A velocity time graph represents the change in an object's velocity with time. This graph shows velocity on the y-axis against time on the x-axis, how velocity changes moment to moment.
Velocity time graphs help us understand how velocity changes over time. A horizontal line means the velocity remains constant. When velocity increases, the graph slopes upward, showing acceleration. The steeper the velocity time graph, the greater the acceleration.
For constant velocity, the graph is a straight line parallel to the x-axis, and acceleration is 0. A shape rule: a flat horizontal velocity timeline means velocity is steady, so acceleration is 0. By heart, a flat velocity timeline means constant velocity and 0 acceleration. A rising straight line velocity time graph indicates velocity increasing with constant acceleration. A shape rule: an upward sloping straight line means the object is speeding up at a steady, constant acceleration. A falling straight line velocity time graph indicates velocity decreasing with constant acceleration. A shape rule. A downward sloping straight line means the object is slowing down at a steady acceleration, which is negative. The slope of a velocity time graph gives the acceleration. A key result. On a velocity time graph, the slope equals acceleration, just as the position time slope gave velocity. By heart, the slope of a velocity time graph equals acceleration. For constant velocity, the slope is 0, so the acceleration is 0. A flat line has 0 slope and therefore 0 acceleration, consistent with constant velocity. Example: acceleration equals 10 minus 5 divided by 20 minus 10, which is 0.5 meters per second squared for an increasing velocity graph. The work. Slope equals 10 minus 5 divided by 20 minus 10, that is 5 divided by 10, which is 0.5 meters per second squared. A decreasing velocity graph gives negative acceleration, for example, minus 0.5 meters per second squared. For a downward line, the slope comes out negative, giving a negative acceleration or retardation, for example, minus 0.5 meters per second squared. The area enclosed between the velocity timeline and the time axis represents displacement. A second key result: the area under a velocity time graph between the line and the time axis equals displacement. By heart, the area under a velocity time graph equals displacement. For constant velocity, the area of rectangle OABC equals velocity times the time interval, which equals displacement. For steady velocity, the region is a rectangle, so displacement equals velocity times time. Example: the displacement between 0 seconds and 6 seconds equals 20 meters per second times 6 seconds, which is 120 meters. The work. 20 times 6 equals 120 meters of displacement. For constant acceleration, displacement equals the area of a rectangle plus the area of a triangle. When velocity is changing, the line is slanted, so split the shape under the line into a rectangle and a triangle. Find each area and add them. Example: the displacement between 10 seconds and 20 seconds equals 50 meters plus 25 meters, which is 75 meters. The work: the rectangle area is 50 meters, the triangle area is 25 meters, so the total displacement is 75 meters. From a velocity time graph, the slope gives acceleration and the area gives displacement. A summary to memorize. For a velocity time graph, the slope equals acceleration and the area equals displacement. This one line is very important. By heart, velocity time graph, slope is acceleration, area is displacement. 4.3. Kinematic equations for constant acceleration. Kinematic equations describe motion in a straight line with constant acceleration. These are 3 ready-made formulas that connect the motion quantities, but only for constant acceleration. With constant acceleration, the acceleration at each instant equals the average acceleration over any interval. Here's why the formulas work. When acceleration is constant, its instant value equals its average value, so we can use one value of a throughout. From a equals v minus u divided by t, we get at equals v minus u. A derivation step. Start from a equals v minus u over t, and rearrange to at equals v minus u. First equation of motion. V equals u plus at. This is the first equation. Use it when you have u, a, and t, and need v, the velocity-time relation. By heart, v equals u plus at. This equation gives velocity v at any time if u and a are known. Its meaning: Knowing the starting velocity and the acceleration, you can find the velocity at any later time. Displacement equals the area enclosed under the velocity time graph, OABD. The second equation is derived from the area under the velocity time graph, a rectangle plus a triangle. Second equation of motion, S equals UT plus 1/2 AT squared. This is the second equation. Use it when you have U, A, and T and need displacement S, the position-time relation. By heart, S equals UT plus 1/2 AT squared. Eliminating T between the first two equations gives the third equation. The derivation idea. Remove time T from the first two equations to get a relation without T. Third equation of motion. V squared equals U squared plus 2AS. This is the third equation. Use it when time is not given. It links velocity and displacement directly. By heart, V squared equals U squared plus 2AS. The five related quantities are displacement S, time T, initial velocity U, final velocity V, and acceleration A. The equations connect five quantities, S, T, U, V, and A. Here's the trick. If any three are known, you can find the rest by choosing the right equation. By heart, the five quantities are S, T, U, V, and A. Kinematic equations provide a mathematical description of how motion changes with time. In short, these equations turn the story of motion into simple algebra. Using kinematic equations, we can predict the position or velocity at a future time. The power of the equations. They let us predict where the object will be or how fast it will move at a future moment. Kinematic equations are valid only when the acceleration is constant, a crucial condition often tested. These three equations work only for constant acceleration. Never use them if acceleration changes. Careful, no constant acceleration means these equations do not apply. In one-direction straight-line motion, distance equals the magnitude of displacement, and speed equals the magnitude of velocity. A reminder, with no turning back, distance equals the magnitude of displacement, and speed equals the magnitude of velocity, so you can use them interchangeably in the formulas. In two-direction motion, the signs of U, V, A, and S indicate direction. When the motion involves both directions, use plus and minus signs on U, V, A, and S to show direction. The signs do the bookkeeping for you. Example 4.8. With A equals -4 meters per second squared and V equals 0, the stopping distance S equals U squared divided by 8. A braking example. Put V equals 0, the car stops, and A equals -4 into V squared equals U squared plus 2AS to get S equals U squared divided by 8. Learn this method for stopping distance sums. At U equals 54 kilometers per hour, that is 15 meters per second, the stopping distance is 28.1 meters. At 15 meters per second, S equals 15 squared divided by 8, that is 225 divided by 8, approximately 28.1 meters.
Everything around us is moving. From tiny dust particles to massive planets. Motion is everywhere in nature. To describe motion, we first need a fixed reference point. Scientists choose a fixed position called the origin or reference point. Now we can accurately describe where the athlete is located. Every measurement of position starts from a chosen reference point. Position is not just about distance. Direction is equally important. Positions on the right side of the origin are usually taken as positive. Positions on the left side of the origin are usually taken as negative. To describe an object's position accurately, we must know both its distance and direction from the reference point.
At u equals 108 kilometers per hour, that is 30 meters per second, the stopping distance is 112.5 meters. At 30 meters per second, s equals 30 squared divided by 8, that is 900 divided by 8, which is 112.5 meters. Notice, doubling the speed made the stopping distance about 4 times larger because it depends on u squared. Understand, stopping distance is proportional to u squared, so double the speed means 4 times the distance. Braking distance depends on velocity, road surface, braking capacity, and driver reaction time. Real-life factors. How far a vehicle takes to stop depends on its speed, the road, wet or dry, the brakes, and the driver's reaction time. This is why it is important to maintain a safe distance from the vehicle ahead. A safety lesson. Because stopping needs distance, always keep a safe gap from the vehicle in front. More gap at higher speed. Vehicle-to-vehicle communication technology, or V2V, warns drivers of possible collisions. Modern tech. V2V lets vehicles exchange signals and warn drivers of possible collisions, and it is being developed in many countries, including India. Motion in a straight line is also called motion in one dimension. A name to remember. Straight line motion is motion in one dimension, or 1D. By heart, straight line motion equals one-dimensional, 1D motion. 4.4. Motion in a plane. Motion in a plane, for example, overtaking, a kicked ball, or a satellite's path, is motion in 2 dimensions. When motion needs 2 directions on a flat surface, it is 2-dimensional or 2D motion, like a car overtaking, a kicked ball's curved path, or a satellite's orbit. By heart, motion in a plane equals 2-dimensional, 2D motion. 4.4.1. Uniform circular motion. When an object moves in a circular path, its motion is called circular motion. Definition. Motion along a circular path is called circular motion. By heart, motion along a circle equals circular motion. For a child on a merry-go-round moving A to B to C, the distance is the curve ABC and the displacement is the straight line AC. Understand it with the example. The distance is the curved path length ABC, while the displacement is the straight line gap AC. They are clearly not equal in circular motion. The distance traveled in one revolution equals the circumference of the circle. One complete round covers a distance equal to the circle's boundary length, its circumference. For radius, r, the distance in one revolution is 2 pi r. The formula: the circumference equals 2 pi r, so one full revolution covers 2 pi r. By heart, distance in one revolution equals 2 pi r. After one full revolution, displacement is 0, because the object returns to its starting point. A key point: after a complete revolution, the object is back at the start, so its displacement is 0, even though it traveled 2 pi r. For time t per revolution, Average speed, v average, equals 2 pi r divided by t. The formula: if 1 revolution takes time t, then average speed equals distance divided by time, that is, 2 pi r divided by t. By heart, v equals 2 pi r over t for circular motion. Average velocity over 1 full revolution is 0 because the displacement is 0. Since displacement is 0 for a full revolution, the average velocity for that full revolution is also 0, even though the object never stopped moving. When an object moves in a circular path with constant, uniform speed, its motion is uniform circular motion. A definition to memorize: moving in a circle at constant speed is uniform circular motion, or UCM. By heart, uniform circular motion equals a circular path plus constant speed. In uniform circular motion, speed is constant, but the direction of velocity keeps changing. Here's the crucial subtlety. In UCM, the speed stays constant, but the direction of velocity changes at every instant. So velocity is changing even though speed is not. As the number of sides of a polygon path increases indefinitely, the path approaches a circle. Understand the reasoning. A square makes 4 direction changes, a hexagon 6. Add more sides and the turns become more frequent, until, with infinite sides, the path becomes a smooth circle with continuous direction change. Activity 4.5. When a marble is released from a ring, it moves off in a straight line. An activity result to remember: when the ring is lifted, the marble does not keep curving. It flies off in a straight line. The marble continues in the direction it was moving at the instant of release. The reason: with nothing to keep turning it, the marble simply continues in the exact direction it had at the moment of release. You'll learn the full reason, inertia, later. The velocity at a point is along the tangent to the circle at that point, in the direction of motion. Very important. At every point of a circle, the velocity points along the tangent at that point, in the direction of motion. By heart, in circular motion, velocity is always along the tangent. A tangent is a straight line that meets the circle at one and only one point. A definition from maths: a tangent is a straight line that touches the circle at exactly one point. Acceleration is non-zero if velocity changes in magnitude, direction, or both. A recall point. Remember, velocity is a vector, so acceleration is present if its size changes, if its direction changes, or if both change. Uniform circular motion is accelerated because the direction of velocity continuously changes. The big conclusion? Even though speed stays constant, the direction of velocity changes at every instant, so uniform circular motion is accelerated motion. By heart, uniform circular motion is accelerated due to the continuous change in direction. In everyday life, we often fail to recognize acceleration caused by only a change in direction. A common mistake: when a car turns at steady speed, we wrongly think there is no acceleration because the speed didn't change. Careful. A change in direction is acceleration too, not just a change in speed. Uniform circular motion is an idealized model, since constant speed and a circular path are often not met. An honest note: in real life, perfectly constant speed on a perfect circle rarely happens, so uniform circular motion is an idealized model. It is still useful as a foundation for real situations like planets orbiting the sun or a vehicle turning. But it is very useful. It is the foundation for understanding real cases like planets orbiting the sun or a vehicle taking a turn. So the model is well worth learning. Motion in space, for example, a car going up a mountain road, a bird, or an aircraft, is motion in 3 dimensions. The final idea of the chapter? When motion needs three directions, length, breadth, and height, it is three-dimensional or 3D motion, like a car on a winding mountain road, a flying bird, or an aircraft. You'll study this in higher grades. By heart, motion in space equals three-dimensional 3D motion.
Excellent work! You have successfully explored the science of motion. From distance and displacement to acceleration and motion graphs, every concept helps us understand movement. But science has many more exciting discoveries waiting ahead. Keep learning, keep exploring, and I'll see you in the next science lesson. Everything around us is moving. From tiny dust particles to massive planets. Motion is everywhere in nature. To describe motion, we first need a fixed reference point. Scientists choose a fixed position called the origin or reference point. Now we can accurately describe where the athlete is located. Every measurement of position starts from a chosen reference point. Position is not just about distance. Direction is equally important. Positions on the right side of the origin are usually taken as positive. Positions on the left side of the origin are usually taken as negative. To describe an object's position accurately, we must know both its distance and direction from the reference point. Let's understand the difference between distance traveled and displacement. The athlete covers a total path of 160 meters, but displacement only measures the shortest straight line change from start to finish. Distance depends on the entire path traveled, while displacement's only on the starting and ending positions. Some objects move slowly, while others move incredibly fast. Scientists measure speed by comparing distance traveled with time taken. Average speed tells us how much distance an object covers every second. The greater the distance covered in the same time, the greater the speed. When an object covers equal distances in equal intervals of time, it is in uniform motion. The speed remains constant throughout the journey. But when distances change during equal time intervals, motion becomes non-uniform. Uniform motion means constant speed, while non-uniform motion means the speed is changing. Velocity is more than speed. It also includes direction. When motion happens in one direction, distance and displacement can be the same. The swimmer traveled 50 meters, but ended where the journey started. Average velocity depends on displacement, not distance traveled. Direction makes all the difference. Acceleration can either increase speed or decrease speed. When speed increases, acceleration acts in the same direction as motion. When speed decreases, acceleration acts opposite to the direction of motion. What happens when we drop an object from a height? The ball keeps gaining speed as it falls towards Earth. This increase in velocity is caused by Earth's gravitational force. Gravity produces a constant acceleration, making falling objects move faster and faster. Acceleration can either increase speed or decrease speed. When speed increases, acceleration acts in the same direction as motion. When speed decreases, acceleration acts opposite to the direction of motion. Acceleration is not just speeding up. Slowing down is also a form of acceleration. Not all motion happens in a straight line. Some objects move in circles. Many objects move continuously along circular paths. The speed stays constant, but the direction changes every moment. In uniform circular motion, the speed remains constant, but changing direction causes continuous acceleration. When an object moves along a straight path, its motion is called linear motion. Many objects around us move in straight lines, such as trains, swimmers, and falling objects. Scientists study straight line motion because it is the simplest type of motion. It helps us describe distance, speed, velocity, and acceleration. Some objects move slowly, while others move incredibly fast. Scientists measure speed by comparing distance traveled with time taken. Average speed tells us how much distance an object covers every second. The greater the distance covered in the same time, the greater the speed. Velocity time graphs help us understand how velocity changes over time. A horizontal line means the velocity remains constant. When velocity increases, the graph slopes upward, showing acceleration. The steeper the velocity time graph, the greater the acceleration. Not all motion happens in a straight line. Some objects move in circles. Many objects move continuously along circular paths. The speed stays constant, but the direction changes every moment. In uniform circular motion, the speed remains constant, but changing direction causes continuous acceleration. We have explored how scientists describe motion using observations, measurements, and graphs. Distance, displacement, speed, velocity, and acceleration help us understand every kind of motion. Whether objects move in straight lines or circles, science helps us everywhere around us. Understanding it helps us understand the world itself. Let's see how much you remember from today's lesson. Can you identify the correct answer? Correct. The displacement is 0 because the runner returns to the starting position. Write your answer in the comments and join me for the next exciting science lesson. Excellent work. You have successfully explored the science of motion. From distance and displacement to acceleration and motion graphs, every concept helps us understand movement. But science has many more exciting discoveries waiting ahead. Keep learning, keep exploring, and I'll see you in the next science lesson. When an object moves along a straight path, its motion is called linear motion. Many objects around us move in straight lines, such as trains, swimmers, and falling objects. Scientists study straight line motion because it is the simplest type of motion. It helps us describe distance, speed, velocity, and acceleration. Some objects move slowly, while others move incredibly fast. Scientists measure speed by comparing distance traveled with time taken. Average speed tells us how much distance an object covers every second. The greater the distance covered in the same time, the greater the speed.